Oh, welcome everyone to this session, and I'll be presenting my work on molecular dynamics of realistic Biochar models with controlled microporosity. And this work is conducted at the University of Edinburgh. So to begin with, we all know what Biochar is, but yeah, I'm gonna bring back the boring stuff. But I want to talk more about what Biochar is from a model aspect perspective. So what we know as Biochar is more of a carbon-rich material, but at the molecular level, we know it to be at a structured material, and is this structure that's responsible for its chemical properties, physical properties, and what that is mechanical properties, which makes the biochar to be responsible for applications like in remediation, for absorption of pollutants, in soil amendment, also for carbon sequestration, and a plethora of many other applications. Well, why this structure is important, some modeling work has been done in the past trying to come up with a model of this material. But however, they have always been modeling as a form of graphitic sheet, which does not really represent what biochar is because we know it to be an amorphous material. And as a result, it's very difficult to link how the structure of a material is responsible for its functioning. So, for example, how does the structure of material how does it affect, for example, how does it affect it, how does it affect absorption? So, is a change of structure is it responsible for change the way pollutants will probably absorb on the material? How does absorption influence? How does it influence the structure? Those are things we cannot really see if we're just looking at the macro scale. But sometimes these changes might happen at a nano scale, which might not be able to see at the level of the lab. So this brings me to the goal of my study, which is to develop and characterize realistic models of wood-derived biochar from molecular dynamics simulation. So let me introduce you what's molecular dynamics. So it's more like a force field method that simulates the time evolution and movement of interacting particles in a system by solving Newton's equation of motion. So for example, you see the way these molecules are interacting amongst themselves. So the way they're going to interact is going to influence the final result of what we get. And in the case of molecular dynamics, an atom is represented by a bit and a bond is represented by a spring. So for us to be able to represent, for example, carbon, the carbon represented by this bit, and then the bond will be this. And it's more like described by a ball and spring mechanism, the way it moves. So it's not they're not rigid, but they do move just as we can see it in the simulation. And this by doing this, it can enable us to understand the structural property relationship of materials. For example, if we want to know like how does uh, how does the structure influence, for example, the mechanical properties or the physical properties of material, this can give us an information of that. Also, like how does interactions on these type of surfaces, how does it happen, what mechanisms are responsible for what we see at the macro scale. And also it can enable us to predict materials properties, so which is the goal of my work. We want to understand like how these models can help the biochar community for further studies, like in predicting material properties, in designing better materials. So for us to be able to come up with a molecular model, what we start by is collecting experimental data like H&C ratio, O&C ratio, aromaticity, like several data from what has been reported experimentally. And we use that information, most especially the H&C, O&C ratio, to inform us on how we can build a structure. So from this information that we get from experimentalists, we're able to build structures, and these structures that's what's going to make the framework of our molecular model, which we call basic structural units. And we use Marvin Sketch to do this. So we're able to control the chemistry of the material. So we don't just build anything out of the blue. We know what's in there. We can control the functionality. We can control control the functionality, the structure, and everything we want by building the structure ourselves. And so doing, we can change so many things. And then after we've built the structure, now we can assemble these different structures into a molecular system. And to do this, what the approach we have, we tend to bring in several different basic structural units together. So it accounts for the heterogeneity of the biochar material. And we do this with the aid of GROMACS, which is a software, molecular dynamics software, which is well known. Well, the force field we use in this case is an OPLS force, which is well known for the modeling of organic materials. So our approach is we get the experimental data, which helps us to get structures, which guides us in choosing building our structures. We assemble these structures into a simulation box. But as we can see, this is just like they are just structures all over the place. They are not consolidated together. And so we apply molecular dynamics modeling with the OPLS force field, which is more like yeah, it describes the interaction between the different building blocks, and the way they're gonna arrange themselves is being determined by that force field, which is more and we use the Lennard-Jones potentials, which is more like 12-6 potential, how they interact, the non-border interactions between these building blocks. And we're able to like condense the material from this process, which is more like we go through a simulated, and it's like we heat the material at a very high temperature, enabling the various structural units to sample the energy space, and then we cool it down. So we move from 1,000 to 700 to 300, and that's how we're able to cool down the material until it gets to a very solid state that's more or less equilibrated. So after we get this, we now try to match what are the target properties we're looking up to. We're looking at the true density and more or less the pore volume. What's the pore volume of the models we've had. Now, if this matches, okay, then we proceed. Okay, we've had a good representation of what we want. But else, if it doesn't match, then we'll go back through a selection loop. So we update back our building blocks and go back through the structure. So we continue this until we get the best structure that more or less matches what we desire. And all of this, of course, the molecular dynamics part is done by GROMACS software. So in this work, I'm trying to model woody biochar that doesn't contain like minimal ash content, because included metals in this OPLS force field is very, very complicated, and it's very difficult as well, like to parameterize it, and we might need like DFT, which is really, really expensive. So we use wood-derived biochar with these properties that we collected from experiment, and we're going to try to build models that more or less have very similar properties to what we want to model. So we've developed two models which we call BCMA. So in this model, we use three different structural units to build this model, and here you can just see the model which has been consolidated here. And we also develop BCMB. You can clearly see like the difference between these two models is more into like this basic structural units, their structure, their functional groups, their aromaticity index. Those are like the aromatic domain size. That's what mostly differs between the first model and the second model. After we've consolidated those two models, and then we try to map them onto the distribution curve of the data we collected from experiment, we're able to see like, okay, what we've had is within the range of whatever which is within the range of the experimental values we collected, which is not bad. And one of the reasons why we are using true density is because the true density is independent of the porosity or any pores in the system. So we're able to know like, is our structure really good? Like the true density gives us information of the structure. If we get a true density which is good, then it most probably means that our models are more or less representative in terms of structure of the biochars we're trying to model. So we went on to characterize the biochar models to get what is the pore size distribution and what is cumulative pore volume. And we can clearly see that for the biochar model A, it's almost like it's non-porous. We can't find any pores. Unlike in biochar model B, where we're able to see there's some pore volume. Of course, in this case, we're talking about micro pore volume. So please let's get in phase. And so we can clearly see like this is really, really so microporous, and there is a need for us to. So it means something should be lacking in our model. It's either we can do it in two ways. We can either change the structures, or we can include something else. So we proceeded to a different approach. So what we did is we used the same because we are having a true density that lies within the range. So what we proceeded is we used the same structures, but then we included virtual atoms. I'm sorry it doesn't show up clearly here, but these small balls here. And then, oh yeah, and then we assemble the system and condense it back just as in the first protocol. So what the role of the virtual atom just acts as balloons, wherein these molecular building blocks will just come around, like they form a framework wherein these structures will condense around it, just like when you're pyrolyzing the material and then the volatile compounds are evaporating, and then in the end, after consolidating the material, after condensing, we remove these virtual atoms, which will now like serve to be the pores, like they'll create the pores that we want in our material, like increasing the pore volume of our material. So that's what we did. I'm sorry, my stuff isn't shown properly because I'm using Linux machine. So that's more or less what we did, and then we try to compare again. Okay, true density is already something good. Are we able to improve on the cumulative pore volume? Are we able to improve on the pore size distribution? So that's what we went into. So we used virtual atoms of different sizes. We first tested these virtual atoms using different molecules to see how they interact with molecules of different shapes, different functional groups, so we can able to understand like how it's going to interact with our about when we start building our Biochar material. So we go through the same iterative approach. So these are two Biochar. This is a Biochar model BCMA, where we use virtual atoms of size 1 nanometers and that of 3 nanometers, and that of BCMB same, and then we use also similar sized virtual atoms. And what we notice is, okay, yeah, the cumulative pore volume increased a bit, and also the pore size increased for both models, which shows that, okay, our approach of creating a Biochar model, so we can actually control we can actually include pores into our system by choosing virtual atoms, which can actually help us control. Like you can see, like the ones with B have have greater pores than that of A, which is also a form of controlling by choosing the size of the virtual atom. Or you can clearly see like the pore volume has increased more than the previous two Biochar models, and we can see the pore sizes as well, which is a good indication for us. So we also yeah, this is also the same for the Biochar model B. We can clearly see like it's a lot higher, as high as 0.155 for BCMB and 0.125 for BCME, which is within the range for what has been reported in literature for those who have given us information for Biochar within this pore size range. And also we're having a pore size of like 2.4 nanometers. Yeah, we're in the pore size range, and yeah, that's what we have mostly been focused on. One thing I want to highlight is the fact like we can have higher pore size, we can have greater pore sizes, but this is within a limitation of simulations. That's if you're trying to create bigger pore sizes, you should be going into more like lattice Boltzmann or meso scaling, and we are not looking yet at that phase. So we're more into the nano scale of this at this stage. Also, we try to look at how the true density, if it, yeah, the true density changed due to increasing pores, like it changed the structure, it changed the way the materials will like condense around themselves, how they rearrange themselves, and we're able to see that, yeah, though it changed a little bit, but then the true density still lied within the experimental range that have been reported in literature. So what we can take away from this work is that we've been able to reduce food-derived Biochar with similar elemental properties, true density, but different basic structural units with using this molecular dynamics. And then we're able to create pores with virtual atoms, like that helped us to control the pore size of of the material we generated. And we can clearly see that the BCMB had higher porosity compared to BCMA, which is mostly because of the structure of the basic structural units. So, and yeah, and we can clearly see that the Biochar model B was able to support these pore structures, unlike Biochar model A, which was mostly produced by basic structural units who were more or less of the same size and more or less very like planar. So what we plan to do for future work for this study, we plan to do adsorption studies of CO2 and nitrogen, which are gases mostly used to sample micropores, and then to study how the diffusion of gases happen in these pores and how they affect the pore deformation in these biochar materials. Well, so the take-home message for my presentation is like what I've been able to understand from this work is like the structural units of the biochar models play a major role in the structural properties, and in particular in supporting the pores in the simulation of the porous biochar model. So with this, I would like to acknowledge my group members and the funding authorities for this work, University of Edinburgh, and yeah. So you can always contact me. These are my details, and thank you for listening. If you have any questions, I'm here to answer you.
Thank you very much, Audrey. That is a very tricky presentation, I would say, for every non-modeler. So if the audience has any questions, please write them into the chat or ask them directly. So there was one question from Karuna. Can you please suggest any book or material to learn DFT, so I guess density functional theory, from the start for biochar?
Well, I don't do the FT. I don't do, but I could. The molecular simulations, honestly, if it's DFT, I really cannot point you to a really good book for DFT. But if for MD, I could, but I don't do any DFTs for now.
Okay.
But I could search that up and ask from colleagues who are in more into DFT and then respond. You can just send me a message on my email, and I will respond to you.
Okay. So the follow-up question was just suggest some MD material, but I think you can do that in the chat afterwards if you have a really good book to point out. I was very interested that you mentioned that the next step is to check the nitrogen and CO2 adsorption.
Yeah.
So would you then be able to extrapolate something about how accurate our current nitrogen adsorption tests are for biochar?
So actually, that's the reason why we want to do that, because there's a recent study that's actually like saying people should be. I mean, the way biochar has been characterized needs to be. I think you're one of those who did that studies. They should be very careful, like, because actually nitrogen might not be able to tell you like the micropores, unlike CO2, and also when you also do adsorption, it also tends to change the this distribution of pores of your material. But that's something that's not mostly taken into consideration. Like, how does that happen? So that's also one of the reasons. That's one of the aims of this study, to see like how does it affect what's been given in experimentally. Like, is there any discrepancy? Does it really give reliable information or not?
Yeah. And then the question that I think we also asked Rosie a year ago or 2 years ago, is there any plan to include the heteroatoms at some point, or some of them?
No. Actually, in this model, we have oxygen. We have oxygen as one of the heteroatoms. Nitrogen is not an issue to include. That's totally okay. The issue is going to be metals like magnesium, because for you to be able to include that, you need to make sure that it's well parameterized, because the interaction between the bond you're going to create, for example, between, let's say, oxygen and magnesium, you have to make sure you have the right bond angle. you have to make sure you have the right orientation, and that can only be done from DFT.
Okay.
Yeah, so to have the right conformation and everything, yeah, it's only DFT that can tell you if that your structure is right or not.
Okay. So
Yeah.
that's your future work after that.
I don't think I'm going. I don't think I'm going to go into any metals. Yeah, it's going to be heavy.
Okay. So the last question from Marshall was, how long did it take to perform this entire set of experiments? And do you aim to use this work to help set standards?
Well, I don't understand what he means, like to set standards. Standards about what? Because I mean, if you want to set standards, it's gonna depend. I mean, I'm not simulating. So there's also one thing I want to clarify. I'm not simulating the pyrolysis process. No. So I'm not simulating pyrolysis. No. I'm just like, it's more like I'm just trying to have a model of the final Biochar model, but not like simulating how pyrolysis is going on. So I don't know if I'm actually catching his question or not.
But then focus on the first one. How long did it take to perform this entire set of experiments? Because it's
Honestly, almost 2 years. It's actually a very long process. Yeah.
okay, so nothing we will do over the weekend, I guess.
Sorry.
Um, nothing we will do over the weekend now. Okay, thank you very much, Audrey, for your presentation.